All right, so now we're going to talk about the normal approximation to the binomial in an actual example. So we're going to use the normal approximation to the binomial to find the probability that at least 70 out of 100 mosquitoes will be killed with an insect spray when the probability of killing them with the spray is 75%. And we're going to use our calculator to calculate the actual probability and then compare it, as well as calculating the normal approximation. So the first thing that we want to do is we want to write the probability that we're being asked to give. So the probability that our binomial that we're being asked for, right, is greater than or equal to 70. So it's very important that we get this right, the greater than or equal to, right? At least means that's the smallest it could be, so 70 is the smallest or larger. Now, what we're being told here is that our probability of success, the probability of killing the mosquito, right, is 0.75, and that we're going to try to kill 100 mosquitoes. So in 100 mosquitoes, that's our n. So what we want to find is n times p, because that's going to give us our mean. So 100 times 0.75, that's going to be our mean. And that's going to be, of course, 75. And then we want to find our n times p times q's root, because that's our standard deviation. So n times p times q. So this is the square root of n times p, I already know is 75, and then that times 0.25. And then I'll need the root of that, which I'm going to use my calculator for. And that is going to give me 75 times 0.25, and then I want the root of that answer. So it's approximately 4.330127. And this number underneath here, n times p times q, turns out to be 18.75. Now it might be useful because then I could get a better answer for this if I needed it to. So now I know all of these different things. Remember that this is mu and this is sigma. So I want to first of all do a continuity correction on this. So what I want to do is I want to take this probability from a binomial to the normal one, so greater than or equal to. So I want to be greater than or equal to 70, right? Here's my 70 bar. Greater than or equal to this 70 bar, remember, is going to include the 70 bar and then go out here, right? So greater than or equal to, I have to start at this point here, which is 70 minus 0.5, or 69.5. So from here to here, I have to do 70 minus 0.5 in order to get that continuity correction. And I'm going to correct that so it doesn't look like 60. So that's 69.5. Okay, now that I have my approximately normal one, I know that x sub n, remember, is distributed approximately normally as long as n times p is greater than 5, n times q is greater than 5, or n is greater than 100, or greater than 30. N's 100, it's greater than 30. I don't have to worry about it. So my mean is 75. And then my standard deviation is 4.33 approximately. So I'm just going to put 4.33 there, and I'm going to draw down there. Okay, so now I'm going to standardize this. So the probability that x sub n minus its mean divided by its standard deviation is going to be greater than or equal to 69.5 minus the mean, 75, and divided by the standard deviation, and that's 4.330127. And now I'm going to find out what my z is. Now remember, I always want you to standardize in my classes, so you'll be standardizing these no matter what. We could just plug that into a calculator and get it automatically, but I don't want to do that. So I'm going to have 69.5 minus 75, and I'm going to divide that by 4.330127, and I'm going to get negative 1.27. So negative 1.27. And negative 1.27, now I could go look that up in my z table, right? That's one place I could get it. So I could say negative 1.27, this is 1 minus the probability of being less than negative 1.27. So I could go down here and over to here, so 1.1012, it's that complement, or 897 or 898 would be my answer there, or I could go ahead and I could put it into my calculator and get it directly. So if I do it with the table, I have to do the probability that z is less than a negative 1.27, and that gives me 1 minus, and that's 0.102. And then that would give me 0.898 and 0. Or if I went for my calculator, I'd be doing the normal CDF. Remember, we don't use the PDF for anything. That's only good for us for drawing pictures, and we don't do that very often either. And on doing this greater than or equal to, I'm going to be starting at this left limit, negative 1.27, right? And then I'm going out to infinity, so e to the 10th, and then comma, and then I can put 0 and 1 in here, but it's not necessary. I could just leave it blank, and then I return. And I'm going to go ahead and do that just to tell you what the value is. And let's see, I have negative 1.27 and e to the 10th, and the value is 0.8979576193, which when rounded to 4 significant digits, the last digit rounds up to a 10 and therefore rounds through and becomes 898, just as we got in this particular instance. So it's the exact same probability no matter what. And so that's our probability of killing 70 or more mosquitoes when we have done the or have a spray that usually kills 75%. Now, the other thing that I asked us to do here was to actually find the binomial probability, the probability that x is greater than or equal to 70 for a binomially distributed random variable. Well, the first thing that I have to do is I have to get what I can use in my calculator, which is for the CDF. So I have to have the binomially probability of being less than 1 minus the probability of being less than 70. But being less than 70, remember, is being less than or equal to 69, because the binomial cumulative distribution function needs values that are less than or equal to. And then I'm going to put into my calculator binomial CDF, because it is the cumulative distribution function. And I have to start out with my sample size, my n, 100, then the probability of a success, which is 0.75, and then my number that I am less than or equal to, which is 69. And then I hit return. And when I do that, I'm getting this part of the probability. And so I'll have to do 1 minus in order to get my answer. So let me do that and tell you what the answer is. So binomial CDF with 100 trials, probability of a success 0.25, and 69 is my value. That gives me a probability of 0.1037. So 1 minus 0.103787. And that 1 minus 0.103787, when I subtract those, I get 0.898. 9, 6, 2, 1, 3. So when I round it off to 0.896, where I would normally round probabilities, then I could compare that to my probability with the normal approximation. My approximation said it's 0.898, so it's 2/1000ths off. That's not too bad considering the time that it would have saved me had I not had a calculator that could just go boop, 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 and there I go. All right, now I think it'd be a very wonderful exercise for you to try this one on your own and then come back and watch my next video. So I'll read it for you. If 23% of all patients with high blood pressure have bad side effects from a certain medicine, use the normal approximation to find the probability that among 170 patients, more than 32 will have bad side effects. So more than 72, probability that my binomially distributed random variable more than 32 have bad side effects. Remember, you'll have to find out what n is, what p is, and then you'll have to make sure that it's appropriate to use the approximation and go ahead and standardize and find that probability.